Okay, any questions? Let's do it. So we were talking about Propertime yesterday, and I say yesterday n minus 1, and then for a boosted observer, you know, if somebody is actually taking this path, right? We have seen that delta tau, or c times delta tau, is what? Square root of minus qm, and I call this vector w, right? Right? Yeah. That's what it is. Okay? So what we're going to do today is we're going to extend this to include objects that are not moving with constant velocity. Because this is the simplest case, and you know, we really cannot do much physics with it. So far we've studied space and time. Now we're going to see how things evolve in space and time. How do particles move? How do fields evolve, and so on and so forth. So suppose you have an accelerating particle. I don't know if I've drawn this accurately enough, because what I mean by that is at all points I would like the forward velocity to be time-like, which means the slope has to be greater than 45 degrees. Let's assume I've done that, okay? So this is a curve. This is a curve alpha of s, and this is the initial point, let's say, initial alpha si and alpha sf. The question is, if someone, and I think I wrote this, but why not? This is t, which is a function of s. All right, so this object is moving in some path. And the question is, from this point to that point, what is, if you were traveling and you carried a clock with you, how much time would have lapsed in your coordinate system? Okay, you are no longer inertial. That is not a constant velocity motion. A force is acting on that, right? You have a jetpack on you. So what do? Well, we do what we always do. We break it into small chunks, okay? Because if it's small enough, gosh, it looks like a straight line. And I don't care about d. But I break it so that the point I'm trying to illustrate here is the direction of the arrow is changing. But for each of this, I'm going to write this. So what I'll do is I will break this into short intervals, short enough so that I can approximate by a straight line. And how many did I pick? These details really don't matter. So I put S1, S2, some Sn, and then final S, F. And then, because of the C, I write C times what, change. It's not C, it's change, and then I put total for the entire path. And I know at this point I'm approximating. So the sums will be converted to an integral for the exact value. And here it is. Oh, yeah, I just described this yesterday. So minus qm of alpha S1 minus alpha Si. I don't know if it's seen clearly. So I'm going to read this out loud. It's minus Qm evaluated on the vector alpha S1 minus alpha Si. So for example, this is alpha evaluated at S1. So it's this vector, this arrow. That's the first. Well, then I don't even need to write it down, but I'll write one more down. What would be the next one?
S2 minus S1.
Good. Alpha S2 minus alpha S1. And then I'll have many. And what's the last one?
Alpha S final minus alpha S1.
Alpha S final minus alpha S n. If I were a wiser man, well, it doesn't look like I am, I would have written this differently. In anticipation of the next line. Ooh, but I can cheat. It's a compensation for not being so wise. Yeah, does this make sense? I just want it to look like a nice derivative and so on and so forth. Okay, that's what I'm headed. I think that's where I'm headed. Yep. So you know what this is. I mean, just one extra term doesn't make a difference. So what I'm going to do is divide this by S1 minus Si squared, and then do S1 minus Si. Can I do that? Haven't changed anything. Over here, so this is in the square root, huh? This is the next line, by the way. What do you think I'll divide by here?
Alpha S final, or sorry, S final minus
S final minus Si squared.
Oh, I see.
Minus Si. Now, why would I do that? Because I can do. Let me look at this guy. Note. And oh gosh, I'm so lazy today, huh? Kind of all kinds of cheating. I'm going to put star. Star is equal. I just want to. I want to. Yeah, I can make it long enough. This way. Minus eta alpha S1 minus alpha Si over S1 minus Si, comma, alpha S1 minus alpha Si over S1 minus Si times S1 minus Si, and I have crossed over to the other side of the universe. Let me see if the camera captures it. Yeah, it does. And so, what can I write this as? Let me make sure my notation is correct. There's no difficulty at all. So then I'm just going to write it. C times delta. Question.
I just have closed parentheses on the eta that you missed.
Correct. Closed. Very good. Yeah. Oh, good. Stuff like that should just endlessly bother you.
It does.
Good. Now look at this. This looks like the derivative of the vector. As S1 approaches Si. Delta y over delta x. Correct?
Is that a comma?
That is a comma, yeah. So it's eta evaluated by the length of this vector.
Yes.
So you have to write it
It's a
twice.
very big comma.
Yeah, very big cup.
That is a very big cup.
Yeah. So, let me write it. Tell me if it bothers you. And I need an integration W. All of a sudden, my approximation has become an equality. In the end, it's a nice looking formula. Yeah? What has happened? These guys became the derivative of the vector, and this became the ds.
And so because of the fact that these are time-like vectors,
Yeah,
you should end up getting a positive in the square root.
correct.
Okay.
Yeah.
So it gets rid of the complex number
It-
that you would have
Yeah,
gotten.
and that's exactly what we did over there.
Okay.
Yeah, that's, here too, we did it exactly because W was time-like. there
And
was
so it'll always be negative anyway. So
It'll
negative
be a
times
negative, yeah.
Makes sense.
So far, we're just saying you have to travel below the speed of light. I mean, I know it's hearsay, but we'll have to. We won't let rumor affect our course, so I'll have to show that to you. Well, you sort of know. If you Lorentz transform gamma is defined to be 1 over square root of 1 minus beta squared. So beta squared can never be 1. So V can never be equal to C. Or even greater, otherwise you get a complex. Is that a nice looking formula? Are you guys happy? Okay. What I'll do is, please remind me, what I'm going to do is I need to show you some properties about proper time. But before I do so, let me do one example. Okay, so in the notes, I have presented the other way around, but maybe I'll go ahead and change. But as I'm thinking, well, this is fine, but what does this mean? So a simple example problem. I'm going to copy down the same example number. I haven't changed it, but these numbers are, it's a sliding scale. Every time I edit notes, it might change, but you should recognize it. Suppose you have an alpha. I think we may have done this. Did we show that this is time-like? No, we haven't. So So this is a curve. The whole point is, I did two things. I picked a curve that's going to be time-like for certain values of s, and for those functions where this is not trivial but not difficult. The point is to illustrate how we do it, not to. What would be the complexity of this problem? An impossible integral. Yeah? But what we want to do is learn how to actually do the problem. So let's find out alpha prime of s. What is it? 3cs squared, 0, 0, 6cs. Okay, so, I notice I've written g, but it's supposed to be eta. Minus 9c squared s to the 4th plus 36c squared s squared, and I can very quickly simplify because it's right in front of me, 9c squared s squared minus 4. So when is this time-like? Oh, I can even do better. F P T when everyone agree or disagree? So but now it's at least when s is greater than 2, this is possibly a potential path for somebody accelerating in space-time. And this object is moving, of course, in time and in the z direction. And why did I pick z? Just for variety. Okay, so I need now tau, the proper time. I'm just going to call it tau. And that's going to be the integral of the square root of the negative. Oh, look at that. Isn't that nice? So the negative just goes away. So I have 3cs square root of s squared minus 4 ds plus some integration constant. We don't, in particular, this is tau. Tau is a function of s. We don't need a dummy variable because I didn't write it as a definite integral. And I picked this, as I told you, because I can integrate this, well, with my book of integrals. Otherwise, I'll be wasting time. So you need to verify that this is in fact true. You would get tau to be actually s squared minus 4, because you can see a nice integration factor over here to the 3s, plus some constant. But it's great to set this constant up to 0, because when the object becomes time-like, tau is 0. Correct? That's when the clock starts. So I'm going to just and that is it. For any s, this is how you get tau. And as I mentioned before, the difficulty is only in setting up the integral. It's not a bad idea for me to re-parameterize this curve so that this s is a totally meaningless parameter. So I'm going to write this as alpha of tau. Well, wherever I see s, I solve for s and stick it back in here. Here, this is not difficult to solve for s. And you'll see when I put it back in, that's what it is. See, 3/2 became 2/3, minus 4 became plus 4, and this is 2 3/2. 0, 0, 3c 2/3 plus 4. This is for now tau greater than 0. So whenever we have these sort of proper time problems, or even we'll see very close to accelerating problems. Anytime you're doing accelerating problems, when you want to compute the force, first thing you have to do is write it in proper time parameterization. S was a meaningless parameter. Okay.
Why is it to the 3 over 2 right there? Shouldn't it just be to the 3rd?
Because
It should just be to the 3rd, right?
yes.
Or actually, wait.
I don't know.
Yeah. And that one on the
Oh, no. That is s squared.
Oh, so you take the square root of it again.
Square
I
root
see.
and then cubic.
I see.
That's
Makes sense.
It had worked out last year. Pretty good. All right, so a little more about some of the properties of proper time. So I will constantly refer to this problem. Anything that we have to analyze proper time over, using proper time, this is one problem already solved. So I'll constantly refer to this problem, and I know that that's the answer. So it's in your notes, but when I write it down, I'll answer it from before. You should, if you're careful, you will check, but I think I've checked this one through. This formula has very nice properties. And this, I think it's, again, continues to be, it is theorem 3, chapter 3, theorem 2. The reason being, I stated one theorem that I did not prove. What was that theorem? I mean, just for fun, we're not talking about this theorem. What was that theorem? If you have any curve in chapter 2, in this chapter.
In this chapter.
Chapter 3.
Didn't prove.
I stated a theorem. I said it's in your notes, but I haven't proved it. And so I'm going to draw a little more exaggerated. And I described it to you. I said,
label it as a theorem?
In the notes I did. In class, I just verbally stated it.
Oh.
The statement is the following. If you have a time-like curve, right? That means its derivative, the velocity, the derivative, alpha prime is time-like everywhere. But the result itself was, if I took any 2 points and drew an arrow, this vector was a time-like vector. I'm just stating it just to remind us. That we won't use that theorem, but that was theorem 3.1, so this is theorem 3.2. But this is important to us. Oh gosh, I have to write it down, right? The proper time along any future pointing time-like curve does not depend on the inertial coordinate system, nor does it depend on the parameter S. I mean, because if you're going to define it as proper time, you want to think of this as an inherently geometric object. If you have an inherently geometric object, you don't want it to be dependent on the coordinate system you chose. It is a clock carried by the observer. Secondly, this S, I told you, is a meaningless parameter. I could choose a parameter, a new time-like parameter called R, and define it to be sinh of S, maybe. That's a freedom that we have. But then the proper time is a physical thing. It's the time lapsed by an observer. So it shouldn't depend on that, okay? So it's easy to show. This part is trivial. And I'm not going to write the proof. Why is it trivial? Look at it and tell me. If I just change the inertial coordinate system, I leave alpha and all of that alone.
It'll be the same answer.
It is eta. Eta is independent of what?
Or not that, but
The coordinate system.
yeah.
It preserves the Lorentz group transformations. So that first part really requires no proof. I would like you to notice that if I change parameter, right? And so I suppose I have, I replace S with a new parameter U. That means U is some function of S or S is some function of U. Then note the following. dx0 of the curve alpha ds is equal to dx0 du dus. So the parameter has to be an increasing parameter, right? So because, okay, I'll let you write that down, and then. Okay, so because the curve is future pointing, this guy is greater than 0. The original curve that was given to you. The rate of change of the time component has to be greater than 0. Because this is a proper parameter, du ds is greater than 0. Correct? It's a one-to-one function. So if s increases, u has to increase. Yeah? So this guy is greater than 0. What does that mean? This guy must be, so it implies that this guy is greater than 0. So first of all, when you write alpha in terms of u, it is also future pointing. There are words in my notes. I'm just giving you the idea. In class, it's probably not a bad idea for you to insert your own words without looking at my notes. Simple mathematically. Is that clear though, everyone? Are you sure this is clear? Yeah? Yeah. Otherwise, it's not an invertible function. Okay. Now I need to show that if I use s over here or u over here, it will give me the same answer. It's not difficult to show it up. So I'm going to do this. C tau equals integral of square root of minus eta alpha, let me write it this way, d alpha ds, d alpha ds, and that's equal to minus eta d alpha du ds d alpha du ds and that's equal to minus eta d alpha du alpha du ds ds. Correct? Because there's two of this, so it's du ds squared, but then there's square root, so I bring du ds. Again, I told you du ds has to be greater than 0, so when you take the square root, you would just get du ds. And this is the change of variables formula from calculus. Guess what this is equal to? Once you're done copying, it's the next line.
Just be, yeah.
It's I'm not dividing. So I started off with the parameter s, and in the u parameterization, the expression is exactly the same. Kind of neat, huh? So the proper time does not depend on the inertial coordinate system, nor does it depend on this arbitrary s. Remember, in the beginning we talked of not having a nice time coordinate to parameterize the path of an object, because t is it's like x, y, and z. It's a coordinate system. So we said we're going to just use an arbitrary parameter. Sure, that works mathematically. But proper time is a physical object. It has a meaning. So that freedom, the mathematical freedom that we have in choosing whatever parameter you want, does not affect physics. This is an incredible feature in modern theories of physics. You have inherent freedom. You can choose any coordinate system or any parameterization, but the physical result does not change. In theories of gauge theories of physics, it is these sort of freedoms where the physics does not change, but you have incredible freedom that tells you what kind of fields should exist in the universe. If you can construct what's called a gauge freedom, you have a theory. And then you can test to see if that theory is realized in nature. You may have, we discovered it by studying electromagnetic fields, that these sort of properties exist. In mechanics, these sort of properties exist as well. But in electromagnetic fields, it just, you go, wow, because it's a field theory and you just get this incredible freedom. And then people started thinking about it. And there's a paper by Yang and Mills, it's called Yang-Mills theory, of generally how to construct these theorems, these theories with lots of freedom, but the physics doesn't depend on those kind of freedom. And then Stephen Weinberg and Abdul Salam, called the Weinberg-Salam model, used this theory to unify the electromagnetic field and the weak field. And it's called the electro-weak unification. This is how we're able to unify fields. We increase we study the largest group where things can change, but physics does not change. So this has a lot, I'm going off on a tangent here. But the point I'm trying to make is these kind of things is easy to see, but there are lessons to be learned. Inherently something is going on. You have a choice of any parameter, and the parameter is meaningless. And then the resulting physics, you get physical quantity that is meaningful. You've seen this before in freshman physics. You've certainly seen this in E&M if you're taking the course with me. Potential, be it gravitational or electric potential, it's only defined up to an additive constant. The electromagnetic vector potential is only defined up to the gradient of a function. So you can change all of this. E and B does not change. Oh, we get to that. Okay. Yeah, this is good. Relativistic. Now that we have time, we know how to define velocity. Well, if we can define velocity, we can define acceleration. Now look at how we're building the story. If we can define acceleration, we can define force. The relativistic velocity u is often written as alpha dot. It's no longer a prime. It really means d alpha, d tau. Not any parameter, but the parameter of proper time. So you take the observer's proper time, and then you find its derivative. And so let me write this out. It is c times dt, tau, x, tau, y, tau, z. I'm not going to write this again. But what do you think the acceleration is going to be defined as? Yeah, so this is just d sky. Yeah. But, I need to change my notation. I'm going to do it, and by end of chapter 3, I'll post all the errors fixed. I've written this as G, U, U. I've told you what's happening, what I have in my mind, but you should see that. I'll fix this. By this I mean. What is that?
Negative.
C squared dt d tau squared.
Plus dx d tau squared.
On one hand, this is what it is. But I'm glad, for once, I will erase this. If I look at that, C d tau ds, and I'm going to square it. So I bring this over here. Is equal to what? Minus eta alpha prime of S, alpha prime of S. So this is minus C squared equals minus eta u. I mean, I take this over here and bring d tau. Correct? So this guy, oh, actually, this is what I want. I started over here, but then I use that. You see what I've done? This is, for example, dt, ds. This is ds, d tau. So it is dt, d tau, dx, d tau, dz, d tau. So if I take the proper velocity, oh, this is called the proper velocity. And this is going to be called what?
Proper acceleration.
Proper acceleration. The interesting property of the proper velocity is that, if you will, the squared length is constant. Oh, sorry, I have two minuses. So the proper velocity has a constant magnitude, if you will, of c. Therefore, what do you think? This is uppercase, huh? Just correct. Proper velocity is uppercase, A is lowercase, don't ask me why. What do you think that is? Huh? Correct? Is that true? Why is this true? Use product rule. First you take the derivative of this, so I'll get AU. Then I take the derivative of this, I get UA. But eta, AU is the same as eta UA. Let me write it out. Let me write it out. I'll erase this part. that true? Eta of xy is eta of yx. We talked about eta being symmetric. So, but the problem is if I do this, I get twice as many. So I take 1/2. But now I go 1/2 dd tau of minus c squared. What do I get? What do I get? I mean, c squared is 3 times 10 to the 8 squared. Taking the derivative of that, what do I get? 0. So look at this. Acceleration, the proper acceleration is orthogonal to proper velocity. You guys are very quiet.
A lot of information.
I'm sorry?
A lot of information.
Yeah, that's true. That's true. Maybe it's a good place to stop, but let me just talk for a few minutes. Let me process this, but I want to conclude one more point. If this is time-like, what is orthogonal to time-like? Space-like. So acceleration has to be a space-like 4 vector. No big deal, there's no meaning attached to acceleration.
There's not a reason why it's space-like, it just is.
It's just, I mean, there is a reason, that's a proof.
That's a
Math is a good reason.
space-like, but why does that mean?
Well, I guess you're kicked in space rather than in time. But that's just finding a different way of saying it.
Does that mean that force is also going to be space-like?
Yeah,
Okay.
yeah.
So relativistic force is not causal.
Force is not causal. It's not a causal vector.
Velocity is a causal.
Velocity is a causal vector. Like I said, I mean, math and physics, you don't get to decide what you want, right? The math has to reveal itself. Nobody can, I don't need to convince you if it's right or wrong. You know, we have to go verify it and see if it has a sound theoretical explanation. And then when you get unexpected news, you just have to learn to live with it. Yeah, as I've said before, this is like, it's like diabetes, you just have to learn to live with it. I mean, you have no control, I mean.
Yes, this is true.
Yeah, it's not what you want, it's not what I'm trying to say is, it's not what you want. Nature just tells you these are the rules. You don't get to pick and choose in physics. There are no. This is a good point. You get to defy the most brilliant mind. When you publish your article. You don't have to bow down to the elders in robes. If you stand your ground, if the math works, if the logic works, and if it's experimentally verified, that's it. You can tumble a giant. You can be the David to the Goliaths of physics. Hey, David? All right, let me stop and I'll take questions.